Let f be a real valued differentiable function on R, the set of all real numbers, such that f of 1 is equal to 1. If the y-intercept of the tangent at any point P, it has the coordinates x and y, on the curve y equals f of x is equal to the cube of the abscissa, haven't seen the word abscissa in a while, of P, then the value of f of negative 3 is equal to. So let's just decode what they're saying. So let me draw a potential f right here. So that's our y-axis. And then let's call that our x-axis. And let me just draw a simple potential f of x. So let's say it looks something like that. I don't know what it looks like. We don't know what it looks like. We just know it's some function, real valued differentiable function on R. So that is f of x. So what is the tangent going to look like? So let's say we have some point here. Let's say we have the point here, which is x naught, y naught. So it's a particular x and y. What would the tangent there look like? Well, it would be a line that has the same slope as the function does at that point. So it would be a line. It would be a line that looks, I could draw a better version than that. It would be a line that looks like that. It would be a line that looks like that. So this line right here would have the equation y is equal to mx plus b. Mx plus b, where m is the slope and b is the y-intercept. Now, we know that the slope is going to be the same as the slope at this point in the function. And what is the slope at that point in the function? Well, the slope at that point in that function is the derivative of the function. So this is going to be f prime of x naught. So we take the derivative, evaluated x naught. That will give us the slope right at that point. So this is going to be y is equal to f prime of x naught times x plus b. Now, if we wanted to solve for the y-intercept, for b right there, we just have to find out some point that's on this line. And we know a point that's on the line. X naught, y naught is on the line. So let's substitute x naught and y naught into this equation and then solve for b. So we have y naught is equal to f prime of x naught, that's just the slope, times x naught, we're just substituting y naught and x naught into this equation, plus b. Plus b. So I just put x naught, y naught into this equation to solve for b. If you solve for b, you could just subtract this from both sides of the equation. We get b. b is equal to y naught minus f prime of x naught times x naught. Now that's the y-intercept of the tangent. And they tell us the y-intercept of the tangent at any point, p, x, y, on the curve y equals f of x, is equal to the cube of the abscissa of p. And abscissa is just a fancy way of saying the x-coordinate. Clearly, they're just using the word to filter out people who don't know the word abscissa. Abscissa just means the x-coordinate. If I tell you I have the point 2, 3, the abscissa of this is just 2. It's just the x-coordinate. So all this sentence is telling us is that the y-intercept is equal to the cube of the x-coordinate. So the y-intercept is going to be equal to the cube of the x-coordinate. The x-coordinate here is x naught. So it's going to be equal to x naught cubed. So for any x naught, y naught on this, or for any x naught, y naught that's on the function itself, we now get this expression. We get, I'll do it in a new color. We get y naught minus f prime of x naught times x naught is equal to x naught to the third. Now, these are particular x and y's, is just for a case of example. It applies to all of them. So we could say it applies to all of the points on the curve. So we could say for any point on the curve, we get y minus f prime of x times x is equal to x to the third. And we know that y is equal to f of x. Or another way of thinking about it is that y prime is equal to f prime of x. So we could write this, and what we're getting here is a little bit of a differential equation. We get y minus y prime of times x is equal to x a third. And we can divide, let's see, we can divide both sides of this equation by x. We get y over x minus y prime is equal to x squared. Just divided everything by x. And then we can subtract this from both sides and then add this to both sides. Kind of skipping a step right there. So we get y over x. Actually, let me write it this way. I don't want to skip steps. So let's subtract y over x from both sides. So we get negative y prime is equal to negative y over x plus x squared. And then multiply both sides times negative 1. We get y prime is equal to y over x minus x squared. And so a little bit of a differential equation here. And when we end solving any differential equations is really a bit of an art. And so we have to think about it. If we could separate the y's from the x's, if we could put the y's all on this side, then it would be pretty easy to solve, but it's not so obvious. And just to give an example, just to inform our intuition, if this was a simpler version, if this was just dy dx, which is the same thing as y prime, if it was just equal to y over x, if it was just that, so if this negative x squared term wasn't there, then this would be a separable differential equation. You could divide both sides by y and multiply both sides times dx. So if you multiply this times dx over y, and you multiply this times dx over y, you would get, these would cancel out, those would cancel out, and you would get y dy is equal to x, sorry, not y dy, you'd get 1 over y. 1 over y dy is equal to 1 over x dx. You integrate both sides of that, and you would get y is equal to x. You would get y, oh, sorry, you would get the natural log. You would get the natural log of y, that's the antiderivative of 1 over y, is equal to the natural log of x plus some constant. And we could write any constant as plus the natural log of some constant, right? It could just be any constant over there. And then you would have, this is the same thing as the natural log of y is equal to the natural log of, when you add exponents like this, that's essentially what a logarithm is. It's essentially taking a product of these two terms. So this would be equal to, this is equal to cx, or that y is equal to cx. Now, this is all just to inform our intuition here. If this negative x squared term wasn't here, then we would be able to solve it pretty easily. Y would be equal to cx. Now, if this term wasn't here, taking the antiderivative of this is pretty straightforward. It would be negative 1/3 x to the third power. So our intuition here is, maybe some combination of the antiderivatives of this and this. And you can't just take them separately, because this y is going to have to be equal to the antiderivative of the whole thing. It's not just the antiderivative of this part over here. But if this guy wasn't here, then it could be y is equal to cx. If this guy wasn't over here, you'd have something to the third power. So just to try things out, and solving differential equations is always a bit of an art, let's just say that y is equal to, we know we're going to have something to the third power in there. So let's call it a x to the third power. And we know we're going to have something to something time, we're going to have an x power in there. So let's call it plus bx. And then let's call it plus c. And that's our intuition, that somehow that this will help get to this term right over here, and that this term, when I take the derivative, will help to get that term over there. So what would be the derivative of this? The derivative of this, y prime in this case, would be 3a x squared plus b. And now what would y over x be? Y over x would be equal to, notice I'm just saying y prime is this. Y over x would be a x squared plus b plus c over x. And so this differential equation here would reduce to, and we just suspect that this might be a solution. This y prime is the same thing as this. So we have 3a x squared plus b is equal to y over x. So it's equal to this thing over here, a x squared plus b plus c over x minus this x squared. Minus this x squared. So minus x squared. So what does this simplify to? If we wanted to solve this equation, we could combine the x squared terms. So let me write it this way. We have 3a x squared plus b is equal to, we have ax squared minus x squared. So that's equal to a, this is equal to a minus 1. This is equal to a minus 1 x squared, a minus 1x squared. And then I have plus b plus c over x. So this is what the right-hand side it simplifies to, and this is what the left-hand side is. And so in this, we have no constraint on b. So b so far can be anything. b could be anything. b could be anything. There's no c term over here. And there's actually, more importantly, there's no 1 over x term over here. So c would have to be equal to 0. There's no c. So c is equal to 0. This term does not exist. There's no c. And then when you look at this coefficient, the 3a, the coefficient of the x squared on the left-hand side has to be equal to the coefficient of the x squared on the right-hand side in order for these two to be equal. So we'd get 3a is equal to a minus 1. Subtract a from both sides. 2a is equal to negative 1. a is equal to negative 1/2. So our hunch paid off. We were able to figure out a's, b's, and c's so that this value for, or this function, does satisfy our little differential equation. And our value we got is y is equal to, I keep using that green color, I don't want to. We get y is equal to negative 1/2 x to the third. That's our value for a, plus b could be anything, plus bx. So this is our value for f of x. And they gave us some information. They told us in the problem that f of 1 is equal to 1. And so we can use that information to solve for b. f of 1 is equal to 1. So when x is equal to 1, y is equal to 1. So we get 1 is equal to negative 1/2 times 1 plus b times 1 is just b. So 1 plus, so we can add 1/2 to both sides, and we get 3/2 is equal to b. So we're now able to fully describe our function. Our function is y is equal to, keep using, y is equal to negative 1/2 x to the third, negative 1/2 x to the third, plus 3/2 x, plus 3/2 x. So that's our function. But that's not what they're asking us. They're not asking us for the function. They're asking us for the value of f of negative 3. So f of negative 3 is equal to negative 1/2 times negative 3 to the third is negative 27, plus 3/2 times negative 3. So minus 9/2. So this is going to be, this will simplify to, well, everything's over 2. Negative 1 times negative 27 is positive 27. And then you have a minus 9, right? This is 27 over 2, 9 over 2, negative 9 over 2. So this is equal to 18 over 2, which is equal to 9. And we are done. This is equal to 9.